Mm. Hi, how are you?
Hi, good morning, sir.
Yeah. How is in India? How are you? You okay?
Yes, we are.
I watch international news every morning. You know, at this moment, number of the infection in India goes up quickly. The huge number of the suffer from the corona.
Yes, sir.
Are you okay? Are
Yes,
you
I'm
okay?
okay. The situation in India is, although patients are increasing, but the situation is very controlled. And
Uh-huh.
yes, government is doing great job by extending hospitals and beds. So accumulate as much
Very
patients, and
okay.
recovery rate is also very good. So most probably
Okay.
the things are going in the right direction.
Uh-huh. 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 So
So
my group has one postdoc from India that he cannot go back to India at this moment. Airport is suspended. Yeah, the very sad situation. Yeah, definitely I want to visit India this time. Okay.
okay.
The maybe next time. Yeah. Please organize in-person meeting, real meeting in India.
So how are the things in Japan?
That is okay. It's okay. This moment the infection almost steady state flat. Of course we can find out 100 people infection per day, but not so much. Very stable. Yeah. Of course the supermarket and the university open at this moment. Everybody go outside. Yeah, last month we had to stay home, but this month is okay.
Excuse me, sir. Hello.
Yeah.
सर 12:30 से नहीं 11 बजे से ही है.
Hmm. Yeah, how many people attend the student chapter meeting?
Yes, sir.
Yeah, how many attended do you have?
Sir, we have nearly
Roughly.
nearly 50 to 55 attendees. So we have 55 registrations. So we are expecting 45 to 50 attendees.
Ah, okay, I see. Hmm. Must be the good big group.
So they most
Yeah.
probably they will join at 11. There's still five, I think five more,
Yeah.
3.
Yeah. I know. I can wait for a while. Yeah, that should be fine. No problem. To talk about my research, wonderful. In such a wonderful OSS student chapter. I like OSS student chapter very much. I frequently visit OSS student chapter meeting that maybe once, twice per year in the world, you know. So this time, unfortunately, that we cannot organize real meeting. Yeah, very such situation. So, but next time, I definitely visit your university, Jaipur in India, of course. And I want to see you the face to face directly the next time to discuss with each other. Of course, we want to enjoy very nice Indian food as well. Anyway, title of my talk, Structured Light Beam and their Applications. Of course, including some part of the biophotonics, but the mostly the fundamental physics of the structured light beam and their application towards the material processing, in particular, including the color structured matter, you know, owing to the orbital angular momentum effect. Anyway, beginning of my talk, I briefly mentioned about the location of the Chiba. How many people have you been to Japan before? I'm not sure. Please send a chat to me, you know. Probably quite far away from India to Japan, the limited number of people come to Chiba could be. So at this moment, my group has one postdoc come from India. So he came to Japan the last year. At that moment, he cannot go back to India at all, you know. That he decided to stay in Japan. I hope he can enjoy himself in Japan, you know. So the Chiba, the eastern satellite city of the Tokyo, physical distance from Tokyo to Chiba is roughly 30 kilometers or something like that. It takes 40 minutes by train. And Chiba has good access to two international airports, Narita and Haneda. Mostly access time from Chiba University to airport, roughly 40 minutes, 50 minutes or something like that, by train or by car. Yeah. The Chiba University is located center of the city, Chiba City. You know, the Chiba, one of the biggest city in Tokyo area. The total amount of the residents is about 1.2 million people living there. So the Chiba University is located center of the Chiba City. At this moment, roughly 3,000 academic working and 15,000 students are studying in our university, of course, including the overseas students come from mostly China, Korea, you know, Taiwan, as well as India. So the roughly 2,000, 3,000 students come from overseas at this moment. The most famous place in Chiba must be, you know, the Tokyo Disneyland. So from our university to Tokyo Disneyland roughly take maybe 20 minutes, 30 minutes by drive from our university. That's quite good location for us. And Disneyland, actually located in Chiba Prefecture, Chiba area, but nobody wants to say Chiba Disneyland. Okay, Tokyo Disneyland more attractive for the a customer from overseas and from domestic area, you know. So anyway, if you have a chance to come to the Tokyo, please step into our university, and of course, I'll take you to the Tokyo Disney. Fortunately, Tokyo Disneyland reopened from tomorrow, 1st July, I think. And my hometown is the western satellite city of Yokohama. So this is also big city. Oh, yeah, okay, you can see the Mount Fuji, you know. So the good location and beautiful harbor city. From Yokohama to Chiba, roughly 70 kilometers far. I catch up a train every morning. It takes roughly 80 minutes, 90 minutes, quite far away from my home to office. Anyway, that I can enjoy myself to traveling from Yokohama to Chiba at this moment. I want to show you this picture. You know, that he is the most famous guitarist, the Brian May. Probably I think the huge number of people watch the movie of Bohemian Rhapsody, even in India, you know. He is a former guitarist of the British rock music band, the Queen, you know. So I had a chance to chat with him, quite a long time, 30 years ago. So I saw him the Imperial College London, in Britain, you know. So at that moment, the vocalist, Freddie Mercury passed away, that he's looking for the replacement of the vocalist. Of course, I like Queen's music very much. I can sing Bohemian Rhapsody. I can play the guitar as well, you know. So I want to be the replacement of the Freddie Mercury. At that moment, Brian May was very positive. Okay, I send message to you. But after that, I haven't received any response from him, you know. A couple of years ago, the OSA has the new idea to release new journal, OSA Continuum. This is a very unique journal, the technical science, open access, rapid publication, yeah, like the scientific report of the OSA version, you know. So the OSA asked me to be the editor-in-chief of this new journal, you know. So after that, already 1.5 years has gone. This OSA Continuum grow up absolutely, you know. At this moment, the publication time must be the fastest. Probably from submission to the publication, roughly 60 days, 2 months. This is the shortest period in the view of the OSA publications, you know. So every year we publish roughly 400 papers from this journal. Of course, you know, Professor Gresham Singh, that he's a member of the associate editor of this journal. You know, if you have interest about please contribute your work to this journal. Of course, we will always welcome your submission. Now, anyway, I want to say, I saw Brian May for a long time. At that moment, I wanted to organize a world tour with him, but it's not realized. But I am always traveling together with OSA Continuum. This is another world tour, I think. In fact, okay, I visit so many OSA student chapters. For example, this is the China Nanjing University. This is the Sao Paulo in Brazil. Okay, this is also student chapter in South Africa. 2018, I went to 6 student chapters. And last year, I also visited 5 student chapters in the world, you know. Total amount of the mileage, 300,000 miles, okay? This distance corresponding to the physical distance from the Earth to the Moon, you know. I want to establish this journal to, at this moment, standing on the moon, you know. Of course, this year, they're quite unusual. I have no chance to visit overseas because corona infection. I hope the corona pandemic that will come down very shortly, you know. I want to visit, of course, in India again to see you and discuss about scientific communication and social communication as well. Anyway, please take care of yourself, and I hope the corona pandemic will come down soon. Okay? Anyway, I would like to acknowledge so many collaborators in the world. Yeah, that of course in Japan and in Australia, Macquarie University, and Korea, KAIST, and Taiwan National Charlton University, and St. Andrews University, UK, and Duke University, United States, and Shenzhen Normal University in China. And I would also thank to the financial support JSPS and JST Crest. Okay, main topics of the structure. Laser was invented 1916, you know. So eigenfunction of the laser beam must be the Gaussian mode, okay? So at this moment, the Gaussian beam is very common in the world. Everybody say, yeah, your laser beam is equal to the Gaussian beam. But that we cannot forget eigenmode family of the several kind of the spatial structure, right? For example, Bessel beam is proposed 1987. Nagel-Gaussian mode proposed by Professor R.N. theoretically 1992, already 25, roughly 30 years has gone. And the Boson beam, this beam including the three-dimensional dark core inside. So the proposed by the Miles Paget in Glasgow University, and the Matthew beam, and the Gaussian beam, and the air beam, also quite interesting at this moment. There are so many people working about such a structure, right, in the quantum optics and classical optics and biomedical application as well, you know. In particular, Bessel beam and Nagel-Gaussian beam, we want to say these family called optical vortices, you know, such optical vortices that exhibit very unique feature. In particular, most important feature must be the orbital angular momentum of light. Such orbital angular momentum must be quite interesting in the view of the material science, owing to the interaction between the light and the matter. I would like to show you several kind of the unique property of the orbital angular momentum of light. Okay. So, optical vortex has so many application fields. Most famous application must be the super resolution microscope with a high spatial resolution beyond the diffraction limit. And space communication is also attractive to beyond the 5G and 6G data communications, and optical manipulation as well, and material processing, etc., 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 etc. At this moment, optical vortex quite hot topics in the world, you know, so many people working about it. So in particular, interaction between the optical field and the matter, the optical manipulation, material processing is quite interesting. Of course, I'm working about such topics based on the structured light and its orbital angular momentum. Okay? In order to understand interaction between the light and the matter, okay, key issue must be optical radiation force. Okay? That we have three kinds of the optical radiation force: scattering light force, absorption force, and gradient force. I briefly mention about the individual force, optical radiation forces. Now please imagine dielectric particle the light beam is coming into a surface of the particle, you know. So optical light field is reflected at the surface of the particle. Like that. At that moment, a part of the photon radiation pressure, the momentum, linear momentum of the light is transferred to the particle. Particle must be accelerated. Okay? This must be the scattering force. Light reflected, scattered by the particle. Particle receive the linear momentum of the light. Okay? Particle must be accelerated. If such a particle has absorption band for the incident light, at that moment, optical field disappear, must be absorbed by the particle. Particle receive total linear momentum of the incident light. The particle must be accelerated well. This method must be the absorption force. You know, the scattering force and absorption force is proportional to the time integrated pointing vector of the light, you know. And of course, optical field is one kind of the electromagnetic field, you know. Direct particle come close to the optical field. Particle must be polarized. Polarized dielectric particle must be trapped by the optical field. This is one kind of the Lorentz force. So in the case of the optical science, this Lorentz force must be called gradient force of light. Okay? That because this gradient force is proportional to the gradient of the intensity profile of the light. Okay. Generally speaking, even by using the high intensity laser, such a scattering force, absorption force, gradient force is quite small value. Normally, piconewton or femtonewton level. Of course, human body, average weight 60 kilograms or something. We cannot be accelerated by the photon radiation pressure at all. But small particle, the size must be the micrometer scale and some micrometer scale. Even metal, the mass 10 to minus 14 kilograms. They're quite small particle. Such a small particle must be accelerated well. Okay? This is the driving force of the optical tweezer optical manipulation. Of course, you know the Dr. Ashkin, yeah? That he awarded Nobel Prize 2018, you know, based on the optical radiation force that is applied to the optical manipulation of the tweezer, you know. He must be the inventor of the optical tweezer. Anyway, such a photon radiation pressure is quite attractive to manipulate small particles, for example, living cell, okay? Quantum dots or something like that. At this moment, the optical manipulation and optical tweezer explore the new direction of the material science. Okay. 1992, Allen, he's a theoretician, you know. He proposed theoretically existence of the orbital angular momentum of the light. Okay? Scattering force, absorption force, and gradient force. This must be based on the linear momentum. Okay? The Allen proposed orbital angular momentum, namely the optical torque of the light. Okay. This is a new breakthrough. Okay? Which kind of the light carried such orbital angular momentum? He say Laguerre-Gaussian mode. This is one kind of the optical vortex structure of light. You know, after that, huge number of people has great interest about Laguerre-Gaussian mode. You know, that to control the orbital angular momentum of the light. So, I would like to show you some small cartoon to understand the basic concept of Laguerre-Gaussian mode, like that. Laguerre-Gaussian mode has such a spiral waveforms. Okay? Pointing vector of the light yeah, is direct towards normal direction of the wavefront, namely the pointing vector of the light inclined to the beam propagation direction. Okay? A part of the pointing vector exists a cross-section of the laser beam. This is orbital angular momentum. Okay. And orbital angular momentum characterized by the winding number of the wavefronts. We want to say this is called topological charge L. This must be the integer. This topological charge comes from the periodic boundary condition along the cylindrical coordinate. You know, the wavefront propagates 1 lambda. At that moment, wavefront must be the twisted 2 L pi. You know, this is the periodic boundary condition. L must be the integer. Okay. We also must mention about a phase singularity of the wavefront. You know, so the center of the wavefront must be has some gap. This phase gap called phase singularity, namely the optical field doesn't exist. So that generally speaking, like a Gaussian mode exhibits an linear intensity profile with dark core. Okay? Now we also can define the hardness of the light, right-handed, left-handed. This handedness of the light is assigned by the twisted direction of the wavefront. Okay? I want to repeat again. So the optical vortex, namely the Lagrangian mode, carried several unique features: handedness, orbital angular momentum, eigenmode property, annular intensity profile. Okay. So such an optical vortex come into the, for example, small particle. What happened? This is a good demonstration. A particle is contained inside the water cell. The particle size is about 500 nanometers, 1 micrometer, or something like that. Okay, the laser beam coming into this cell. Particle aligned to the ring start to rotate. In this case, clockwise direction. This is orbital angular momentum effect of the light. Okay, that we can directly control the orbital motion of the particle by using the orbital angular momentum of the light. This must be quite interesting. Okay. So, optical vortex in classify the Lagrangian mode family and Bessel beam family. Okay, what's different between the Lagrangian mode and Bessel mode? This is a Helmholtz equation in the paraaxial approximation. Under the paraaxial approximation, at that moment, eigen state of the light must be the Lagrangian mode. You know that this IL phi must be the azimuthal phase. This must be the origin of the orbital angular momentum of the light. Okay. So the typically intensity profile must be the like donut, something like that. In the case of the Bessel beam, you know, Helmholtz equation, baryon separation, you know, so the wave function can be written by the product of the radial direction, azimuthal direction, and propagation direction independently, you know. The laser beam, the light field propagates into the space. Radial amplitude, azimuthal phase doesn't change at all. Okay? We want to say this is a non-diffraction. In this case, you know, the Bessel beam, of course, has annular intensity for the dark core, but it also exhibits multiple rings. Okay? Lagrangian mode Bessel mode carry the orbital angular momentum. This is same, but the intensity profile and beam propagation slightly different. You know, how to distinguish Lagrangian mode and Bessel beam? Quite simple. You know, at this moment, the laser beam, Gaussian mode, comes into. Okay? We put on the vortex plate. This is some phase plate, has a lambda gap at the center. You know, as azimuthal thickness slightly change continuously, it has some gap. This gap corresponds to the lambda. Okay? At this moment, the wavefront passing through the vortex plate, we can generate rugged Gaussian mode. This rugged Gaussian mode focused down by the Achicon length. Achicon length must be the the shape must be the triangle, you know. So the laser beam is compared to the rugged Gaussian mode to the better Gaussian mode. Okay, now quite easy. Now we want to have to use Achicon length. This must be the like the blister. Okay, the triangle that rotate along the azimuthal direction must be the blister or something. Okay, quite simple. That we can easily convert rugged Gaussian mode and Bessel mode. Of course, we can convert Bessel mode to the rugged Gaussian mode quite easily. Anyway, such optical vortex has several kinds of applications. The most famous application must be the fluorescence microscope. Yeah, just generally speaking, scanning of fluorescence microscope, spatial resolution limited by the pump spot size, namely the diffraction limit, even by using the laser sources. Okay? So the typical spatial resolution is about 500 nanometers, 300 nanometers, that roughly determined by the wavelength of the light sources. Okay? At that moment that we observe the fluorescent signal from the pump region like that, we assign individual element inside the living cell. But generally speaking, living cell including some small element, you know, nanoscale element. So such a spatial resolution is not enough to distinguish individual small element inside living cell. That we must improve the spatial resolution significantly at that moment. Pumping overlay the optical vortex. Optical vortex suppress the fluorescent signal from the living cell through the stimulated emission depletion or highly excitation, you know. So that we can expect fluorescent signal just come from the central dark core of the optical vortex. Okay, so the dark core, size of the dark core is almost nothing, you know, very small, 1/10 of the optical field, you know. So we can expect nanoscale spatial resolution by utilizing such a simple technique. Now, this technique is proposed by the Professor Stefan Hell Max Planck Institute, that he is Nobel Prize winner, 1914 in the chemistry. Okay? Though he has demonstrated the spatial resolution less than 20 nanometer by using the visible light in the scanning fluorescence microscope. This is a one good demonstration, you know. So this is a conventional fluorescence signal microscope. By using such a donut beam overlaid onto the pump beam, the spatial resolution is significantly improved, you know. You can identify the individual dot onto the cell, you know. This is also good demonstration to observe vessel, you know, inside living cell. The beautiful picture. He said spatial resolution of the fluorescence microscope is not determined by the lambda over MA at this moment. You know, if we increase the intensity of the vortex beam, we can improve further the spatial resolution of the fluorescence microscope down to the 10 nanometer, less than 5 nanometer, less than 2 nanometer. You know, this must be the one breakthrough to observe the small particle directly by using the visible light. The most key issue of the optical vortex must be the annular intensity profile. at that moment. Okay? This is another kind of the interesting biomedical application. At this moment, he used the vessel beam. Vessel beam exhibit non-diffraction, okay? Light sheet coming like that inside cell. Okay, that we can observe the cross-section of the laser beam. That we can directly observe the fluorescence signal by the objective lens by side view. Two-dimensional fluorescence signal can be captured, okay, directly. So the seed that may be going down, going up, that we can observe the three-dimensional, the fluorescence signal of the living cell directly, okay? This must be another interesting application of the structured light. And we mustn't forget, you know, the space division telecommunication system. This must be the quite promising application of the structured light. Okay, so of course now is that we perform presentation onto the Zoom. Okay, that many people want to access the internet. Data capacity is limited. That we want to thinking about the 5G, 6G, 7G, yeah, to increase data capacity of the telecommunication, yeah. So optical fiber telecommunication already reach up to the upper limit. We must thinking about how to break the data capacity of telecommunications. One solution must be Nagel-Gaussian mode, carry the digital data, telecommunication data, together with the Gaussian. That because optical Nagel-Gaussian mode is eigenstate inside the fiber, even propagate inside the fiber quite long distance. Of course, propagate inside the air quite long distance. Intense profile doesn't change. Okay? This must be useful for telecommunication system. Of course, huge number of the researchers are performed to investigate such a space division telecommunication system based on the Nagel-Gaussian mode, you know. They expect data capacity reach up to the 100 terabytes per second. Okay, beyond the 5G. So initially, this technique is proposed by the Alan Wheeler. He's a former president of the USA. Yeah, this must be the quite attractive application. So key issue of the structured light must be the eigenmode property. This property must be quite useful for the telecommunication system. Okay. So the spatial resolution, super resolution microscope beyond the diffraction limit are quite attractive, of course. The space division telecommunication system also quite attractive. Yeah, that to achieve the new social, new advanced sociality, you know, that with beyond the 5G, 6G, you know, okay? But we want to directly utilize orbital angular momentum light to the material science, okay? So we apply such a structured light to material processing. We proposed this idea that already 10 or 20 years ago, 15, I'm not sure, over 10 years ago. Why the laser material processing is interesting? So, late 1980, high power laser, based on the CO2 and neodymium laser, you know, we can achieve the new technology, welding, drilling, scribing as well, you know. This must be at this moment standard platform of the automobile industry. And late 1990, the ultra-short pulse laser based on the Titan Sapphire and the fiber laser become commercial. We achieve three-dimensional microfabrication. Okay. If we add new parameter of the light of triangular momentum to the laser material processing, absolutely we can add new value to the material processing, definitely. What kind of the new value? We expect something like that. Okay, basic concept is quite simple. We pump the target by using the optical vortex, like a Gaussian mode and Besson mode as well. Okay, the surface of the matter must be the melted and vaporized. Melted matter and vaporized matter considered at some micron scale cluster. They should receive orbital angular momentum of the light, start to rotate clockwise and anti-clockwise direction. Okay, and after that, they cool down again and pile up on the surface to create such a twisted microstructures. Okay? Why such a twisted microstructure are attractive? You know, the chiral plasmonic devices must be very popular to characterize chirality of the molecule, chirality of the living cell, and so on, so on, so on, you know. The new technology must be based on the chirality must be quite attractive in the view of the material science. Chirality is quite a universal concept in the material science at this moment. So even by using the advanced chemical processing, sometimes difficult to achieve such a chiral structure onto the nanoscale and some micron scale. Such a laser material processing based on the optical vortex is quite attractive. We performed a huge number of the demonstration of this technique. So this technique is quite interesting. All experiments can be performed in the atmosphere and room temperature. We don't have to utilize vacuum chamber and cryogenic atmosphere. In the view of the cost saving, energy saving, quite attractive. Okay, we published so many papers. The first paper, 2010. After that, we published over 20 papers concerning such optical vortex material processing. Okay. I would like to show you several unique features. This must be the tantal, this must be the copper, silicon, polymer, gold thin film. Okay, all material is twisted onto some micron scale. Quite beautiful. And of course, the twisted direction of the structured matter can be controlled directly by switching the handedness of the light sources itself. Right-handed optical vortex like Gaussian mode create right-handed structured matter. Left-handed like Gaussian mode create left-handed structured matter. Quite interesting that we can distinguish handedness of the structured matter 100%. Okay? This must be quite unique, the material processing technique. Okay. In fact, the recently Russian group demonstrated chiral plasmonic nanojet by illumination of the vortex beam onto the silver thin film. Okay? Now this demonstration quite beautiful. They can create such a twisted needle onto the surface of the silver thin film. Okay? The published paper 1970 from the Optics Express. Okay. This is a Canadian group, University of Ottawa. I'm not sure how many people know that his name Kokam. Kokam is a famous researcher of the high field physics. You know, their group performed some experiment. Femtosecond vortex pulse illumination and nanostructuring of the silicon. They say chiral needle structure appear onto the surface of the silicon by optical vortex illumination. That with a pulse duration 345 femtosecond based on the titanium sapphire laser. Okay, this must be also quite beautiful demonstration. Okay. Another interesting demonstration performed by the Japanese group. Yeah, they use single X-ray vortex pulse with femtosecond pulse duration. They can also create twisted needle onto the substrate of the multi-layered semiconducting material, you know. And this is also Japanese group, the Osaka University. They utilize spatial light modulator and create two-dimensional array of the spiral surface structure by the optical vortex array. Such a demonstration is quite interesting. I like them very much. But I want to say such a demonstration must be the just follower of our research. The first demonstration performed by ourselves. So such a structured matter formation by the optical vortex illumination become very popular at this moment. Huge number of groups has interest about how to fabricate such a kind of structure on the sub-micron scale and nanoscale. So at this moment, the audience must be the student and early career researchers. I want to say to you, yeah? So of course, that we must respect friend, but that we also thinking about some competition in the view of the research with friend, So most important issue must be the originality of the research to overcome such a competition. At this moment, I would like to show you one game changer for such a competition. What is a game changer? We want to think about orbital angular momentum to spatial solid and beyond. Okay? Yeah, we performed the experiment by using optical illumination. At that moment, we can control the morphology of the surface of the matter, The inside of the material doesn't care. But that we can combine the spatial solitary effect and orbital angular momentum, we directly control the morphology of the inside matter. Okay, this must be the three-dimensional structured matter formed by the orbital angular momentum transfer effect. Okay? Self-lighting waveguide. This is a very interesting technology, The laser beam, ultraviolet laser beam focus onto the liquid phase pure resin. Okay? At that moment, the resin is polymerized. Polymerized resin has relatively higher refractive index. Okay? So the laser beam is confined inside polymerized resin. Okay? At that moment, optical field confined inside resin. So the polymerized matter grow up like the fiber. Okay? So optical field is guided inside the fiber. And this must be the self-lighting waveguide. Mechanism is quite simple. The UV light attack, photoinitiator attack, monomer and oligomer cross-links, polymerization occurs. At that moment, polymerized matter has relatively higher refractive index. Optical field must be confined to like the one kind of the non-linearity of the spatial solitary effect, self-focusing effect. The general speaking, like the optical field suffer from the diffraction effect. But diffraction effect can be compensated by the self-focusing effect. At that moment, spatial form doesn't change, even pass through the long propagation. We want to say this is a spatial solitary effect. Okay? Such a spatial solitary effect in the photopolymerization, namely the self-lighting waveguide performed by the conventional Gaussian beam. If we utilize, the optical vortex, what happens? This is very curious question. This project performed by our group and St. Andrews group, the St. Andrews University group in the United Kingdom, Professor Kishandrakis, And we want to less the scattering loss, absorption loss of the light field inside polymerized matter. We replace UV light by the visible light. Yeah? So we decided to use 532 nanometer green laser light sources. The wavelengths coincident with the cut-off value of the absorption band. At that moment, we can expect less absorption loss of the light field inside the fiber. Of course, longer wavelengths, can reduce the scattering loss as well. Okay, we can extend the photopolymerized fiber, by the laser light injection. This is the experimental setup. We prepare the very simple experimental setup. UV, the 532 nanometer green CW laser. The laser beam is converted converted into the aggregation mode by using the spinal phase plate. Laser power roughly 1 watt. Okay, the aggregation mode directed towards the cell, including the liquid phase Cuban regime, by relay optics. Okay, photopolymerization is observed by the CCD camera from the side view. This CCD camera can record the growth of the fiber inside cell. We also want to observe transmitted light from the fiber waveguide by using the conventional CCD camera from the top view. Okay. So we perform the 2 experiments. At first, we use an aggregation mode. Second experiment is quite simple. We introduce action lens here. We pump this cell by using the bezel view. Part difference between the aggregation mode and bezel view. Okay. I want to show you beautiful movie, the self-lithium helical fiber. At first, I would like to show you the aggregation mode case. This is a side view of the cell, and this is also top view of the cell. This movie must be synchronized. Okay, the laser beam is coming into the aggregation mode, pass through the fiber, but transmitted light distorted significantly. The length of the fiber is limited up to roughly less than 500 micrometers or something like that. Such a fiber must be not so much beautiful. We just replace the laser light source from the aggregation mode to the bezel beam. Everything is drastic change. Okay, the fiber is created. The laser beam propagated inside the fiber. Transmitted beam still exhibit donut intensity profile. Okay, a bezel beam twists the spatial soliton to form the helical fiber with the fiber length over the centimeter scale. Okay, and this fiber can deliver optical vortex field, namely the bezel beam. Okay, such a fiber must be useful for the local communication. Yeah, the individual optical devices for the space division multiplexing telecommunication system, of course. Okay. So this is an optical image of the fiber, fabricated fiber. Okay. The length of the fiber over 1 centimeter. Maximum size is about 2 centimeters or something like that. I want to show you magnified image of the fiber. This fiber twisted. Okay. The pitch of the twist is about 250 micrometers. This interval determined by, bezel beam propagation. So at this moment, that we will publish one paper from the optics letters very soon concerning such a bezel beam self-lithium helical fiber with a centimeter scale length. Okay. So such a spatial soliton effect can be simulated by using the nonlinear simulating equation like that. The very beautiful simulation without such a simulation without can support well our experimental result. Okay. Another topic, slightly biomedical photonics here. The cyanobacteria and human red blood cell, okay? They're quite interesting material for the biomedical application. They exhibit relatively higher refractive index rather than the water. Yeah, for the visible light, for example, green light. Okay. So the green light passing through the cell, including the cyanobacteria and human red blood cell, such a bacteria and cell can be collected by the photon radiation pressure of the optical field. The such a self-organized waveguide based on the biomedical material is formed. Okay? This is also one kind of the spatial silicon effect. Quite attractive. Biomedical material work as an optical waveguide for the red light sources. How to apply it, I have no idea. But in the view of the fundamental science, quite interesting. At this moment, we apply the optical vortex to such a biomaterial instead of the Gaussian beam. What's happened? At this moment, we utilize bacterial adoption. This is much tough optical field, in comparison with the cyanobacteria and blood cell. Okay, that it exhibit high optical damage threshold. Okay, to avoid photobleaching of this bacterial adoption, we use 1 micron near infrared light sources. At this moment, that we can fully compensate thermal effect this by bacterial adoption itself, And we also utilize the solvent D2O instead of the CH2O, that we can fully suppress the thermal issue inside the bacterial adoption suspension. At first, that we inject Gaussian beam. Okay, this is a self-focusing effect. The laser beam pass through the bacterial adoption suspension. Self-focusing effect happens. The small spot is observed onto the CCD camera. We convert Gaussian beam to the optical vortex by using the spiral faceplate. What happened? Quite interesting. Okay. You can see that twin mode. Yeah? Optical vortex. Lagrangian mode passing through the bacterial adoption suspension. At that moment, Lagrangian mode converts to the twin mode. And twin mode is rotated clockwise direction and anti-clockwise direction. This rotational direction is determined by the hardness of the Lagrangian mode. Namely, I want to say this is a spinning spatial solid. Okay? If we remove the bacterial adoption from the suspension, nothing happens. Okay? Such a twin mode creation and twin mode rotation must be originated by the interaction between bacterial adoption in optical light field with OM. Now we are thinking about following model, Optical field collect bacterial adoption molecule by the photon radiation pressure. At that moment, orbital angular momentum transfer from the bacterial adoption, such a spatial solid must be rotated, So such a twin mode, spinning temporarily. Now, quite interesting dynamic that we can understand the interaction, fundamental interaction between the optical field and biomedical matter, This is the final topic of my talk. Okay? Laser in this world mass transfer. This is a new technology for the microfabrication of organic material. For example, we prepare the donor thin film. This donor thin film pumped by the laser from the backside. Donor material is break into the fragment, and fragment fly away. We catch up a fragment by using the receiver substrate that we can pattern the donor material two-dimensionally. Unfortunately, this technology, that's quite interesting, but unfortunately, that we cannot control the direction of the flight of the fragment at all. The spatial resolution of the patterning is not so much better than the conventional inkjet printing. Okay, how to improve the spatial resolution of this technology? we apply optical vortex. Basic concept is quite simple. Okay? Donor thin film exists. Okay, we pump this is donor thin film by the optical vortex pump. At that moment, orbital angular momentum transfer from the optical field to the matter donor film. Donor film must be twisted. This donor film eject droplet. Droplet also spinning. Such a spinning motion of the droplet can stabilize straight flight of the droplet itself. We can pattern donor material onto the receiver substrate with high spatial resolution. This is true or not? At first, we pump the donor field by the Gaussian. At this moment, donor material has very high viscosity, over 4 Pascal per second. This viscosity is correspond to the honey drop, or mayonnaise. Generally speaking, such a material is not available for the inkjet printing technology. Okay? We pump this film by the Gaussian beam. Okay, film break into the many fragments. Fragments fly away. Okay, that we cannot control the flight of the fragment at all. Just replacement of the light source from the Gaussian to the optical vortex, namely the Lagrange Gaussian mode. Okay, film create blister home to the spinning jet, After plateauing instability, this jet eject single droplet. The volume of the droplet is roughly picolitri level. Okay, this is correspond to the conventional inkjet printing technology, limitation of the inkjet printing technology. Okay, such a technique must be quite useful for the spinning, tronics, the flexible electronics, and so on, many directions. Why such a phenomenon has happened? Optical vortex can melt the donor film. Donor film is deformed. At that moment, donor film receives the orbital angular momentum from the optical field. Okay, they start to twist, and jet is created. At that moment, jet is also spinning. Orbital angular momentum transferred to stabilize straight flight itself. Okay. We published one paper from the optics express last year. That recently we demonstrated some patterning technology by using this technique. Beautiful pattern can be created. That, for example, this is OH. Such a micro patterning based on the optical vortex laser in this forward transfer must be utilized for the drug injection onto the human bodies and so on. Okay. The structured light optical vortex can twist material. This is quite simple, okay? But it offers a new twist of the fundamental and applied material science beyond the conventional light sources, Recently we published 2 articles as a review article from the Advanced Optical Materials Journal of Nanophotonics, if you have interest about, please visit the website and download the PDF file, okay? And we regularly host international conference in Yokohama, very beautiful harbor city. This time, so that we decided to cancel the OMC 2020, but we want to expect that we can host optical manipulation and structured material conference in Yokohama next year. Of course, I welcome you to join us, I want to see you in Yokohama in person, definitely. And we also host another interesting conference, Molecular Nanomachine, sponsored by the SPIE in San Diego. This is also canceled. At this moment, this conference is scheduled online. But next year, we want to organize a conference in person. Please join us. Okay. So if you come to Japan, of course, we can enjoy scientific discussion after the session. That we want to invite you to such a karaoke session. You know that this is Japanese social communication. So I hope you can enjoy scientific discussion and social communication in Japan. Thank you very much for your kind attention. Okay.
Thank you very much, sir, for this knowledgeable session and a great webinar. I, on behalf of OSA Student Chapter MNIT Jaipur, really thank you so much for
Thank you.
accepting my invitation in such short time and giving such a knowledgeful webinar sessions. So we can take some questions here. So all the participants can also raise
okay,
questions.
Please send the message to me. Yeah, please send it to me. Please send your message to me. Then I directly send back everything for you. Yeah, okay?
So, can you answer these questions which are directly coming?
Okay, this one? Okay. How important do you think optical manipulation and modulation is for optical computation? Wow. Okay. So I have no idea the question, but you know, optical manipulation and optical modulation, they're based on the photon radiation pressure, quite attractive to the maybe new generation of the optical computing, for example, quantum computing and so on, you know. So there may be we can thinking about some structure that has some opportunity to contribute to the optical computing and enhanced computing speed as well, of course. This must be a good question. I send back my message to you. Okay, thank you.
Thank you, sir.
Okay.
So there is one more question.
One more question. Yeah, of course. The fantastic question, you know, does structured light support surface plasma polarity? Yes, absolutely yes. At this moment, new topics must be the concept of orbital angular momentum conservation law, between the light field and the plasmonic surface plasma as well. This is a new topic, of course. So the structured light convert to the structured surface plasma as well, and structured surface plasma convert to the optical field, namely the structured light. Such an interaction between the plasmonic, the surface plasma and structured light, at this moment, new trend of the research field. This must be quite interesting. Of course, if we can convert structured light to the surface plasma polarity, you know, that we can make downside optical field onto real nanoscale, so that we can expect some interaction between the optical field in the nanomaterial directly. That must be quite interesting, of course. Yeah.
Thank you, sir.
Yeah, okay. Very nice meeting. Yeah, I want to see you directly next time, of course.
Definitely, sir. We also, I also want to, you know, on behalf of, you know, OSA Student Chapter, we also want to see you here as soon as this pandemic is over.
Absolutely. Absolutely.
We want to
yeah, it's okay. Yeah, the next time I definitely visit your institute, and I want to see you face to face. And I would like give my best regard to the Professor Singh. Singh must be here. Okay.
Yeah.
So, yeah.
Hello,
Okay.
hello, Professor Umasu. How are you?
I'm very fine. At this moment,
Yeah.
the number of the infection, the flats in Japan. So the university is open, and of course outside city should be fine. That we can go to restaurant and we can go to pub, etc. But Tokyo area slightly severe rather than the other place. The Chiba is okay. Yokohama is okay. No problem. Yeah.
So
The please visit to.
Chiba is towards the airport?
Yes, indeed, indeed. Yeah, that at this moment, airport, the temporary suspended. So that maybe the very limited number come from the overseas to Japan. But within a couple of months, we want to reopen the airport again, That of course, a Professor Singh come to Japan. Of course, please visit our university, definitely, yeah,
Yeah, sure.
I want to see it. Yeah.
Anyway, Professor Masu, on behalf of our chapter, and I hope our host and the student have taken care of all the logistic to make this webinar possible.
Yes,
to see you
of course.
Sometime in our campus also.
Of course.
Maybe in future,
of course.
when this,
of course.
we will be get rid of this pandemic. So hopefully we will invite you in person.
Okay, absolutely. Absolutely, it's okay.
We have,
absolutely,
we have few more chapters nearby to our university. So
really? Okay.
Okay. Yeah. So
I love to visit India very much. Yeah. I love to visit India very much. Yeah. I like Indian food. Yeah. The last time I visited India, just a couple of days. Yeah. I want to go back to India. Absolutely.
So don't worry. When we will invite you, we'll make you more foodie. We'll give you more and more.
Oh yeah.
Don't worry. So anyway, thank you for.
Thank you.
This webinar, and
hope
to be in touch with you soon. Thank you very much. Thank you.
Yeah, of course.
Ankit.
Thank you very much. Thank you.
Thank you all the attendees who have attended this webinar. And
okay, thank you very much.
We'll try to
I am very happy. Yeah. Okay. I could enjoy myself very
good.
much. Yeah. Wonderful. Yeah. Okay.
Good.
Thank
Good
you.
Everyone.
Yeah.
Bye-bye.
Yeah. Bye.
Ankur, meeting को over करो है ना, and I'm leaving now. Thank you.
Okay, thank you, sir. So thank you very much, all the participants. So we have already sent a feedback link on our WhatsApp group. We are also mailing that feedback group. Please give your feedback, and you will receive your certificate as soon as you submit your feedback. Thank you very much. From OSS Student Chapter, MNIT Jaipur. Thank you.